Okay, so it's great pleasure to have Yegor Zenkevich from Moscow. So he's gonna tell us about structure of elliptic Ding-Iohara-Miki algebra. Please.
Okay, thanks Satoshi for inviting me. It's a great pleasure to give a talk, though by Zoom, but makes our audience more like international probably. Okay, so I'm going to talk about a generalization of a deformation of Ding-Iohara-Miki algebra. So let me first introduce the algebra itself, which we are going to deform and discuss. So this is the algebra, which is a deformation of central extension. So it is denoted by, I will denote it by UQT of GL1 double hat. So the meaning of this is that if we have double hat, we have double loop algebra and double central extension. So these two hats stand for double loop or toroidal algebra plus double central extension. So there are two central charges in this algebra, and there are two loops, which are completely, the algebra is completely symmetric in them. And then this QT are deformation parameters, quantum deformation. So the definition of the algebra, it's for the definition of the algebra, let me draw a small diagram here. So since it's a double loop algebra, there is a double grading. So we have the grading by modes of these two loops. So I can introduce currents, which have two indices, the generating currents, and they sit in a lattice, two-dimensional Z2 lattice. So this is the idea of what are the generators of the algebra, and then what are the relations? Well, there is no completely satisfactory way to write all the relations of the algebra explicitly, because they, well, if you have two generators sitting at 2 points, in general, well, there is no direct way of writing the commutator in the on this lattice. Sometimes you can, and it happens when, well, there are some complicated restrictions. When you have a vector here and a vector, for example, here, then the triangle formed by this these two vectors, it doesn't contain any interior integer points, and also it doesn't contain any integer points in the middle of the edges. So for such pairs of generators, there is an easy formula. This there is an easy definition, which is a nonlinear. Well, I will write some formulas in a moment. But for two general vectors, if they are somewhere in the lattice, I don't know, a vector here and a vector here, for example, well, you have to re-express them through more elementary generators to obtain the commutators explicitly. Like the algebra is actually generated by just 4 elements: this one, this one, this one, and this one. So then you can commute them and obtain the whole lattice. Plus there are 2 central charges. plus two central charges, C1 and C2, which are from this double central extension. So let me introduce the generating currents for this algebra. So there will be x plus minus of z and psi plus minus of z. So these are built from J. So x plus minus, they sum all of these generators here, and x minus, they sum all generators here, like the column at +1 and the column at -1. So we have +-1 here, m and z minus m. This is the psi plus minus generating currents, and the x plus minus, the psi plus minus, they are exponents of sums with n bigger or smaller than 0, and here we have hn z minus m. Okay. So this h generators, h plus minus, they correspond to this and this part of the generator. So you see that basically they contain the generators which generate the whole plane, but then there are additional generators inside the generating current. So in principle, it's an extra some extra information. One could generate the algebra with smaller number of generators, but it will be convenient. Sorry, so here I should write J 0 n. Right? So which and like will be another name for h plus minus n, and this guys will be x plus minus m. So this generating currents, they satisfy some commutation relations, and I'm not sure that it's very elucidating to write them, but let me write some of them. For example, I have x plus of z, x plus of w, and here is there is a structure function, so the so-called structure function. Well, the structure function is written like this. It's a third order function. Something like this. So, yeah. And there is a set of relations for the currents, like along this line. Sorry, so minus plus. So there is a similar relation for psi plus minus with well, for example, I can write plus minus here, and there is a similar commutation rule for psi with x with another bunch of this g functions. And the most important, so let me write some of the relations. So this is a bit technical, but unfortunately this algebra is complicated. There doesn't seem to be any simple way of defining it without writing all this stuff. So this G small function is expressed through G plus minus. Like this, etc. There are lots of like for any pair of currents there is the corresponding relation, and the most non-trivial of them is the relation between x plus and x minus, which reads like this. There will be some delta functions on the right hand side. So I have here I have and here there are two delta functions which should be understood like this. I will explain in a moment. So what are the first? What are the gammas? The gamma is one of the central charges. So the first central charge, gamma is the exponent of this first central charge. Then what is delta? Delta is sort of analytical continuation of delta function from the unit circle. So explicitly, it's the following series, formal series. So that's the delta function here, and everything else I think I have defined. So there are relations. There is this structure function, and there are relations for this algebra. So why should we care about this algebra at all? Like what is what might be the reason anybody is interested? This algebra plays a role in gauge theories and in string theory. So in gauge theories, for example, let me write it here. So this algebra, it acts on the moduli space of instantons, acts on the key theory of the moduli space of instantons. For example, if I have, well, if I have mkn and sum over k, and I have a qt equivalent k theory. So I have this instantons on C2, and I introduce the omega background action of U1 times U1 here, and then I can have equivalent K theory. I can study equivalent K theory of this moduli spaces. In principle, it's a complicated business, but we know, like many people studied it, and we know that there is so that this space is actually a Fock space. Of just a free chiral boson. So that in particular, it's elements are enumerated by Young diagrams, right? So here sit some states, lambda. Well, there is an additional gauge parameter u, like that's the equivalence with respect to the global gauge transformations. And this becomes the momentum of this state in the Fock space. So this space is a representation of this algebra. So this algebra acts on this space, on this Fock space, which I would like to call Fock space with this QT inverse. And it is a representation with central charges C1. So let me better write it with gamma, which is the exponent. So C2 is equal to 0, and gamma is equal to T over Q 1/2. So and then in this representation, one can write this current in terms of the creation and annihilation operators. So here I have AN, the free boson operators, which act on the Fock space, and then I can write these operators using this ANs. And basically the identification. Now I'm going to write some formulas up to proportionality. So basically HN plus minus should be proportional to AN, this creation and annihilation operators. There is some coefficient in front, but let me not write it. So this H plus minus N, what is the idea? How do they commute? Let me redraw my diagram. And I have my H plus minus generators sitting here. So it turns out that on this plane, for every slope, for every rational slope, I have a Heisenberg subalgebra. And the central charge of this Heisenberg subalgebra. So for any slope here, I have some, if it's rational, then I have some points sitting here. And the corresponding generators, they commute if I denote them by J and M. Then let's suppose that I have some slope AB that's rational, are coprime. Then I have the generators AN, BN sitting here, and they satisfy for general slope. They satisfy the Heisenberg algebra like this. Sorry. I have to erase something, sorry. So the commutation relations are like this. I have some prefactor, which depends on A and B, and depends on Q and T. But the important part is that there is this delta here, and the coefficient in front of this delta is related to the central charges, C1 and C2. So here I have basically exponent of AC1, exponent of BC2 minus exponent of the inverse, like this. So you see that the central charge, so here, if I have the slope, which is sort of parallel to this C2 equal to 0, then this J is commute. So basically, if I have a horizontal slope and I put consider my generators which sit here, they all commute. While for vertical slope, they don't commute because C2, so this is the exponent of C1, because C1 is non-zero. And since C1 is non-zero, then there is a Heisenberg algebra spanned by these vertical generators, Hn. And here they are just these ANs, which act on the Fock space, and we know that they satisfy the Heisenberg algebra like this. The problem is then to express this x plus minus in terms of AN, also in terms of this AN. And in this representation, so we have x plus minus of z, they're equal to certain vertex operators. Vertex operators acting on F. And they also depend on AN. So there are some exponents of AN, of the free field, basically. So it is instructive to consider the limit when t is equal to q. This is called the unrefined limit. And in this limit, the algebra simplifies a lot. Like there is an explicit way of writing the generators in this case. So let me do just this. So, and then I comment on this representation. So I have J and M, JKL equal to the following expression. There is antisymmetric SL to Z invariant pairing in the power here. Like this. So here are the two central charges, and well, here is a subpart, well, which tells us that the commutator of these two is proportional basically to the area of this triangle. So this expression is basically the area of the triangle, where this one is. So this is 0, this is NM, and this is KL points. And as you can see, it's a Lie algebra in this case because it's linear in the right-hand side. However, for general T, it will be a nonlinear deformation. It will be a quantum algebra. So there will be, in the right-hand side, there will be nonlinear pieces also. So in this case, it's actually easier to write the expressions for this generators x plus minus. Let me do this. So again, J. So this H plus minus N, they are still like this, but x plus minus, I can give explicit answer for the vertex operators. So it's phi of z minus phi qz plus minus, normal ordered. So basically, that's the answer for the vertex operators, where phi is the free field. So this is the idea. Plus there is this log z times log u, where this u is this u. So what is the idea? This is the representation of this algebra, because what it does is actually it adds or removes instantons. So that's a non-perturbative algebra which adds or removes essentially BPS particles, like instantons, and that's why I think it might be interesting. That the physical relevance of this algebra, about which I think I have no time to talk. So that's a subject of another story. Why it is relevant and what does it mean in gauge theory and string theory. So here I would like to report on another development, which is about the elliptization of this algebra. So this is also relevant because in that case it acts not on K-theory but on elliptic cohomology of these modular spaces, and correspondingly it corresponds. So here it is related to five-dimensional n=1 gauge theories, and in that case it corresponds to six-dimensional theories on torus. And there is for example, there is a version of the AGT correspondence, which is basically the correspondence between gauge theories and their instanton modular spaces, and some algebras, some like the correlators of vertex operators, basically a little bit like this. And this algebra, of course, plays the central role because that's what this algebra is what acts on this modular space. And in the elliptic case, it acts on the elliptic cohomology, and there is some elliptization of this vertex operator. So that's what I'm going to talk about. This is now I'm going to erase this, and I'm going to define the elliptic deformation of this algebra. So let me first like announce what will be. Okay, so let me take. So here will be elliptic deformation of this algebra, and I will add here some p. So it acts on the elliptic cohomology, probably. And there is still, well, the representations we'll discuss a little bit. So this is a joint work with several people. It's well, you have to look at 2012. Well, it's not 2012, right? It's the December of 2000, but the number of the paper is like this. And it's a joint work with Jan Kozjaz and two of his students, Mohamed Ghanem and Kerem Kurshun. So that's a joint effort. So the idea is that this new algebra, this elliptic algebra, the function, the structure function g plus minus of x, recall that it was something like this, a rational function. there is an obvious elliptic deformation of this function, where here there will be theta functions. And you see, actually, it shares many characteristics with this function. For example, if I take x inverse, then I basically exchange the sign plus minus here. So anyway, one can define the same algebra with this structure function. The only difference will be that here with this J0n, there will not be this restriction to positive or negative part. So there will be twice as many J generators. Let me write them again as H plus minus n. So here n is not restricted. You see, I have twice as many vertical generators. So I have here H plus n. But on top of that, for every n, I have H minus also. So this vertical column is sort of doubled. And it's, well, let me draw it like this. So I have the H plus minus, there will be twice as many of them. And then it is needed because you see here in G, it can be expanded in positive powers of x. So it's a polynomial in x. However, here with theta functions, this is a Laurent series in x. So this x is related to this z, this spectral parameter. So I need both positive and negative parts for this z. So for this algebra, I have to introduce additional modes here, which tend to 0 as p goes to 0. So when p goes to 0, in this limit, the algebra should turn back into the trigonometric algebra. And in the limit p goes to 0, this additional generators, so hn plus with n less than 0 and h minus with n greater than 0, they go to 0. Well, that's one way of understanding it. The other way is that they just decouple from the algebra. The commutators, or they decouple. You can just say that the generators are still somewhere, but they never interact. They commute completely with the trigonometric piece of the algebra. And you are left with what I have already described. Okay. So let me not write the technical details, because the formulas, as you have probably seen with this definition of the dim algebra, the formulas are not really memorable. But the important point is that the representations of this elliptic algebra, they are known to resemble the representations of trigonometric algebra. However, there are some differences. For example, in the same case, if I have this gamma non-trivial and C2 equal to 0, I have a representation not on a Fock space of a single boson. I have a representation on the sort of double Fock space. Then I have F, a representation F tensor F, and I have here a boson AN and I have a boson BN. generating these two pieces. So the states here are enumerated by pairs of Young diagrams, and the spectral parameter U. So why it happens? For the simple reason that there are twice as many vertical generators. So if you want to say that this algebra contains non-trivial central charge, then both of them will have non-trivial central charge, and they will act as twice as many creation operators. But otherwise, I can, well, the formulas for the representation are quite similar. There is even a kind of algorithmic elliptization procedure where if I know the trigonometric expressions, I can put P inside them and make them elliptic. So basically this means, so the elliptization, there is, from the works of theta, it is known that there is a kind of elliptization algorithm where if I have something like this, an expression like this in the trigonometric case, trigonometric expression, this is can be made elliptic by writing something like this. So this P is this P, you see, and basically what you do is you add this 1 minus P, and you also add this BNs, and they come with you see that the relation between these two powers is different. So here it is n minus n, here is m and n, and this amounts to this Laurent part of theta. So you have sort of wrong powers in the correlators of this current. So they are somewhere. They will be somewhere in exponent, and well, the rule will be like this. So you also see that you have this 1 minus Pn, which corresponds to this thetas being expressed as cube or hammer symbols, because so here you can write theta like this, and this can be written as an exponent. Something like this, so probably minus. So you see you have this 1 minus P in the denominator. So this is the elliptization procedure, and from this one can, if there isn't this kind of algorithm, one sees that probably there is some simpler way of looking at this algebra. So the idea is that this algebra is in fact isomorphic to the trigonometric algebra. So the deformation, well, there is this deformation, but the deformation is just a funny way of rewriting the trigonometric dim algebra. So the main result is that this elliptic algebra is equal to trigonometric algebra plus a Heisenberg algebra, which is vertical in this picture, this additional generators. And this explains why the representations are so simple. That's obvious because you can express them through trigonometric representations plus representations of the Heisenberg algebra, and then the only way which ties these two algebras are the central charges. If I have C1 and C2 here, then here I have C1. So the central charge is shared by these two algebras. So you can say that it's a sum factored by the relation that the central charges are equal. So that's the story. But then, well, it's still kind of a miracle because you have to get this elliptic functions, and you have to rewrite all the relations with this elliptic function back into trigonometric expressions. So, for example, let me show you how it works. Let me see how much time do I have. Okay, let me better explain. So let me better explain why there are twice as many generators, and I explain another way of looking at this algebra, which will probably explain why there is this sum. So this is the story of Thermo-Filled Double. So another way of looking at on this elliptic algebra, at least there is, if I have representations, I can have intertwiners. Of representations. And this is known to correspond, so let me explain for the trigonometric algebra, the intertwiners of representations, of Fock representations, for example. They're refined topological vertices. So if I draw these representations according to their the slope of the central charge, so here I draw the like 1, 1, 0, 0, 1. This corresponds to the Fock space with the central charges. So this corresponds to a line 1, 0. And then there is an intertwiner like this. And it's a well-defined operator. You can solve for an intertwining operator here, and it turns out to be equal to refined topological vertex, and you can build this networks of these intertwiners or webs of these intertwiners. So what happens if I make a circle to take a trace like this over the Fock space, over this horizontal Fock space? Well, one way of understanding it is that I have intertwiners of trigonometric dim algebra, and that's it. Like I don't. Well, that's one way of looking on it. A trace, the first way is to understand it as a trace of intertwiners of trigonometric representations of the trigonometric algebra. And the second way is to say that there is, it's not a trace, but a vacuum matrix element of intertwiners of elliptic algebra. So it will look like this. I draw a special double line. Sorry, so the horizontal line is doubled, but there is no trace. So how do I why there is this second view on this picture? Well, the second view corresponds to doubling the bosons here. So here is a Fock space tensor Fock space. So there are A and B acting on this line, on this horizontal line. But there is this vacuum vector here. So how do I understand the relation between the two? The answers, they are the same. Well, up to some prefactors, the answers for matrix elements are the same. It coincides with the trace. So with the trace, you can deform this picture like this. You can look at it like as if this loop was passing under, like this. So you see, this is a state on which this picture ends, and this is a dual state. And then I have this horizontal line going here, and this horizontal line going here. So I have essentially this double line. That's the way to understand this double line. And there are two, I can say that there are two bosons. Here I denoted by AN and here by BN. So there is a Fock space here and Fock space here. And I have a space in the tensor product of these Fock spaces. However, if I look at it here, this state doesn't look like vacuum. Because here, if I take a trace, well, first of all, I forgot something. So I have Q to the power D1, which is the grading operator. So this D1, it counts the grading. It counts this vertical grading. So this is the standard expression, like a character. I have this expression like this because I have here. This will be my psi star, and this will be psi. These are the intertwining operators, and I take a trace as I write. So I have this Q to the power D1, and I'm going to split it into two pieces. I can write it as a product of Q power D1 half sitting here, and Q to the power D1 half D1 sitting here. So what kind of state is this? This is a famous state in a tensor product of two Fock spaces. It's called a Thermo-Filled Double. So what is this? This was discovered in ancient times by people who studied just thermodynamics and statistical physics. The idea is that if you have a state in a Fock space, and then you want to compute an average of an operator with a thermal density matrix, something like that. This rho is exponent of minus beta h. So this h is going to be d1 in our case, and exponent of minus beta will be q. So this q is in the algebra is the p parameter. That's the role of p parameter. So let me write this like this. So here I have an elliptic algebra with this p parameter. That's where its origin lies. And it's possible to write it as an average of a certain thermal state So that's a thermal, what is called a thermal vacuum, or the Thermo-Filled Double. So this state is in the tensor product of two Fock spaces, and every state comes with its pair. So what is this? This is really a sum over states with the exponent of minus beta times energy. So suppose I expand in the eigenstates of energy, and it is written like this. Well, this expression, for this expression, I have to know what is a thermal vacuum. And the thermal vacuum I define like this. So this is my definition of this thermal vacuum state. Next, I have my operator. And I have another state. So you see this identity, this n and m, there is just scalar product of them. So I suppose that they're orthonormal, and then this nm is equal to delta. So the double sum becomes a single sum, and these two become equal. So I get back my expression like here. So that's the starting point of this Thermo-Filled Double technique. So you have this state which looks unfamiliar, but that's really the state which is here, where like the exponent of minus beta will be p, essentially. The next part, and the essential part, is that one can transform the state using a Bogolyubov transformation. Значит, can make a Bogolyubov transformation so that this state becomes a vacuum state. What does it mean? It means that I have my thermal vacuum. This thermal vacuum is equal to some unitary matrix in a tensor in a tensor product of spaces acting on the vacuum. And this matrix is going to depend on beta, obviously, but it's unitary. So I can say that my state is a unitary transformation of the vacuum. But the other way to put it is that my operators, or my creation and annihilation operators, which sit inside O and in the Hamiltonian, they can be transformed with this U beta. So I can say that I have AM, which will be transformed like this, and this will be the thermal operators, and these thermal operators will annihilate the vacuum, right? The positive generators will annihilate the vacuum. So now that's the scheme which works here. So I have the vacuum of this tensor product Fock space. So really, it's a tensor product of two vacua. And I can understand that I essentially do the Bogoliubov transformation in this Fock representation, in a pair of these Fock representations. I essentially do this transformation. And it turns out that this precisely works for this relation between the compactified network with the trace and the vacuum matrix element of an elliptic algebra. So these two are precisely related. And this points out a way of rewriting the operators of elliptic algebra in terms of the operators of trigonometric algebra. So that's basically the way to obtain, that's a hint to obtain a rewriting of the algebra in terms of elliptic algebra in terms of trigonometric algebra plus the Heisenberg. So this Bogoliubov transformation is what tells us how to rewrite. We have H plus minus n elliptic. This will be our thermal AN, and somehow it should be related to Hn plus minus trigonometric. But as I said, there are twice as many of these guys. So I need to add some G plus minus n, also trigonometric, which will form the Heisenberg an additional Heisenberg algebra. So this Bogoliubov transformation sits here. So there is a way of rewriting these generators in the algebra. And though we have the hint came from a particular representation, this Fock representation, the rewriting is completely general. So you can look up the formulas in the paper. The explicit formulas, they are just for the generators of the algebra. They are abstract. It's an abstract statement that the algebra generated, the elliptic algebra generated by these generators is isomorphic to the algebra, the trigonometric algebra generated by these elements plus the Heisenberg algebra, like this one. Okay, so that's the end of my talk. Thank you for listening. So I expect some questions maybe.
Thank you very much.
Thank you.
Question from audience.
Hi, may I ask a few questions?
Yeah.
Go ahead.
Jean-Emile. Yeah, nice talk. Yeah, I have a few questions. So you explained what happened for the elliptic deformation of the Cartan currents. What with X plus minus? Do you address them with some vertex operators? Or
right. That's the technical part. There is addressing. So that's the kind of where all the blood, sweat, and tears went. So you have to dress them, and there is a way. So let me write the formula. Well, let me. Okay, I can actually write the explicit formulas for all the generators. So we have suppose. Well, let me. I'm going to as follows. So I have this Hn plus minus elliptic, which I just denote by Hn plus minus, and I will have this I will denote by the trigonometric ones will be Hn tilde, and the plus and the minus are just correspond to n positive and negative. So there is really in trigonometric case there is no need to have plus and minus separately. So I don't use this index, and the rewriting of elliptic generators through the trigonometric is like this. Oh, sorry, it's vice versa. So that's the Cartan part.
Mm-hmm.
And okay, and the other factors, the dressing factors are like this. So these are the factors by which one has to multiply x plus minus.
I see.
And the other one is very similar, but with this gn. Like this, and then x plus minus elliptic is related to there are some proportionality constants, but these are just C numbers. So it's funny that this factors for plus and minus, they are the same. So let me check 1 moment. Let me check if I didn't miss anything.
I just to have the rough idea. I mean, if there is a typo, it's not a big deal.
Yeah, so, yeah. The idea is like this.
So it works also for C1 equals 0. This.
Sorry, for which?
For C1.
Which variable? Yeah. It works always. So you see, it's plus gamma here. So when gamma is 1, it's 1/2, and it works. You can check. So for any representation, you can check this. There are a bunch of representations. You have this vector representation, of course, of the elliptic algebra. There are this fork. The horizontal, so-called horizontal forks, which are double representations on a double fork space. So it's encoded by a pair of Young diagrams. And there is a vertical representation. This is funny because for vertical representations, those generators which are doubled, this vertical piece which is doubled, they actually have 0 central charge, so they commute. So the Heisenberg algebra acts trivially because it's commutative. It's just, you can act with a number, but like you can set it to 0 consistently. So this one is on a single Young diagram. That's because here the Heisenberg algebra is this one, which is not doubled. And this is consistent. There is this vertical representation on a single Young diagram. It can also be written like this.
But do you still have Miki automorphism that exchange the two, or because then
that's a good question. So how can one understand the Miki automorphism? Because you have well, when I introduce this additional Heisenberg algebra here, the second one, I explicitly break the SL to the invariance. Because this vertical thing, it shares the vertical central charge with the algebra. So I pick one direction, but otherwise I can well, now the algebra is not so symmetric, but still it retains some symmetry. After all, you have this trigonometric algebra, which does have Miki automorphism. So you just have to ensure that you have this additional Heisenberg algebra acting in the proper way. So it acts differently in vertical and horizontal representation because you have more or less okay, so something like B and BM is equal to is proportional to C1, something like this. So this C1 is either 0 or not. That's a choice. And also there is a more, if you want to know all the truth, that there is the Hopf algebra structure in the elliptic case, and this we haven't proved, that the Hopf algebra, the elliptic algebra as a Hopf algebra is isomorphic to trigonometric algebra plus the Heisenberg, because it contains it's a non-standard Hopf algebra structure. It's not just a sum of two Hopf algebras. So it's something different. There is a twist which involves both of these parts. So it somehow, the Heisenberg part somehow also takes part in the coproduct.
I see.
So that's an interesting problem to understand this cycle with which it is twisted, the coproduct.
I see. Actually, I have another question. If you deform the commutation relation of your Heisenberg algebra, a priori you should be able to obtain more general Ding-Iohara algebras, now with different structure functions.
Yes.
Yeah.
Yeah.
Could you have some interesting?
You mean if I write some different g of x, right?
Yeah, typically, yeah.
Yeah, I haven't tried. So, well, definitely there are different. There are different options. It's not just the elliptization is a single way which one can do. Just the elliptic algebra, it like caught some attention of the people, and I really wanted to fix this. Like, what is really the place of this algebra in the framework of ordinary trigonometric algebra. So here, yeah, there is a question. If this thing, I think that if this thing is linear, then it will be, it basically corresponds to loop algebras, UQ of G hat, a single hat. I think, I'm not sure. If it's, well, if it's square, this is no, for example, like if it is a square, then it is something like GL2 double hat, or that's because SL2 is non-simply laced, and then you have double factors here. But in principle, you know, there is a whole family of this quantum toroidal algebras which are parameterized by toric manifolds. So there is an infinite number of them, and they all have particular structure functions which are encoded in the toric diagram. There was a paper by Dima Galachov and Masahito Yamazaki recently, where they do everything on the Youngian level. I don't remember the number, but it was about a year ago.
Yeah.
So they write the relations for this algebra, and they write the representations, and they have all sorts of different structure functions, I think. Well, at least they have a variety of algebras which all look like quantum toroidal, but they're encoded in the toric diagrams.
But in terms of cohomology of quiver varieties, would there be some other interesting case to study? I think there would be also some interpretation.
Yeah. So they correspond. They know how to write quivers. That's basically this case. So that's when you write it's still a restricted case. But when you have a toric diagram, you can draw a dual. You draw a dual something like, I don't remember, something like this, a dual quiver, and using this quiver, you write the algebra. The algebra is more or less on quiver representations, if I remember correctly.
Nice.
But that's, of course, that's a restriction. In principle, you can have arbitrary quivers and try to write algebras, but that's, yeah, I'm not sure I can say anything about the completely general case.
Okay, well, thank you. Thank you very much.
Any other questions? So can you tell me a little bit about this refined topological vertex and intertwiner? What do you mean intertwiner of the Fock space?
Yeah, so you have a tensor product of two representations.
Mm-hmm.
And then you have
two representation means the parameterized by two Young tableau, you mean?
You have a space, yeah, you have a space F tensor F, where the states are labeled by tensor products of Young diagrams. So these are the two diagrams sitting here. So they sort of collide, these two representations, and then there is an operator psi which eats these two things, and it spits out. It's a linear combination of states in this third representation. So you have matrix elements C lambda mu, which depend on Q and T, and this is the refined vertex. And then what does it mean to be an intertwiner? So for now, I just wrote some operator with some coefficients. The intertwiner means that it commutes with the action of the algebra, so that if I have any element of an algebra, and it acts on the tensor product. So then delta, it will be the same as acting.
Is it delta is the coproduct of the Hopf algebra, as a Hopf algebra?
Yeah, yeah. So this is the coproduct of dim algebra.
I see, I see.
So the simplest case is, again, if you have if T is equal to Q, the unrefined case, then this delta is nothing but then delta of G is G tensor 1 plus 1 tensor G. That's Lie algebra, the Leibniz rule. But still you have to, still this operator psi is non-trivial, and we know that's the unrefined topological vertex, because the action on lambda and mu is different. One of them is the vertical representation, another is horizontal representation. So the action on them is of the same element is different, and then the operator psi is also a non-trivial operator.
I see. I see.
It's a bit, this psi is a bit like vertex operator. If you have it's not exactly what you would call a vertex operator in a vertex operator algebra, but it a little bit resembles. So if you have the vertex operator algebra, for example, you have some affine algebra G hat, and then you have here you have a highest weight representation with some weight omega, and you have some central charge K. Then here you have some omega prime and the same central charge K, while here you have some evaluation representation with central charge 0 and with some, I don't know, with some third weight. And then this corresponds to a vertex operator acting. So this will be equal to some V parameterized by omega double prime, sitting at point Z. So it's evaluation at point Z. So something like this. Here it's a bit different, but the picture resembles. And also this vertex operator, it satisfies exactly the same equation, except that the representations are again. So the representations of the algebra, they are the evaluation representation and the highest weight representation. This is also.
Okay.
So something like this.
Okay, thank you very much.
Okay. Thank you.
Any other question from audience?
Actually, if I may ask another question.
Go ahead.
Yeah, sure. Yeah, sure.
So, I also wanted to ask, so you studied GL1, how about higher rank? Do you have a similar property of factorization with Heisenberg?
I suppose that it should be similar with, instead of Heisenberg algebra, you would have an affine, quantum affine. So I suppose that I didn't study this, so maybe this is all wrong, but I suppose that this is should be isomorphic to like the trigonometric plus the piece which is quantum, well, quantum affine somehow. So there should be GLN single head. And here Q and T, I don't know like what kind of parameter should be here. There's a question mark. This is some Q prime. So I think that there is, you know, that inside this GLN double head, there are two quantum affine subalgebras.
Yeah, right. Yeah.
Just as like you have horizontal and vertical.
Yeah.
And one of them will be doubled. So that's the conjecture.
Ah, I see what you mean. Ah, I see.
And actually, there is a little bit similar effect, because it is known that if you have an elliptic, if you erase, so here, if you erase one of the heads, you have UQP, GLN head, and there is a known relation to, you just have trigonometric one plus some zero modes, more or less. Here you have something like UQ GLN, like quotation marks.
Yeah.
Well, there are some works about this elliptic algebra which claim something more or less like this. So you have there is an isomorphism, and the only missing piece are some zero modes which more or less form this GLN. Like you have to add some P and Q zero modes. That will be the necessary addition. So basically, they have the same argument, just one head lower.
Then could it be possible to double both the vertical and horizontal subalgebra somehow? Would that make sense?
That's a very good question. I don't know the answer. So the idea is that this is some double elliptic story, and it should be related to the double elliptic integrable system.
Oh, nice.
And the Miki automorphism should be regained back. But I don't know how to approach it, because, well, the elliptic dim algebra, some clever people like theta have just defined it before us. So that's one way. Just you get something which is known, and then like transform it into another something which is known. So here, if you double everything, then the algebra is not known. So how do I approach it? I'm not sure. Like what should I transform into what? That's a good question. But it's extremely. I suppose that the situation is it's possible that the situation will be much more difficult in this case. I'm not sure, but I think that it might not be as easy as in the elliptic case, in a single elliptic case, because it is known that the double elliptic systems are very complicated. Like that, it's not kind of it's not a linear evolution from the ordinary elliptic.
I see.
But I haven't tried, so maybe it's easy.
Okay. Well, let me know if you try. I would like to know the answer.
Yeah, but I have suspicion that it is hard.
Yeah, yes, you might be right. Okay, thank you.
Okay, so then let's thank the Yegor.
Okay.
Um,
Thank you very much for the invitation.
Yeah.
And for the question.
I will stop